Hello, all, and welcome to this new series on MPLS. So, in this series, we will learn what MPLS is, why was MPLS created, where is it used in today's world, and how is it being implemented with other routing protocols like OSPF, BGP, and also how using MPLS we are implementing L3 VPN. So in the later part of this series, we will also learn about L3 VPN. We'll also learn what is a route distinguisher, what is a route target. So we will be also learning how BGP makes use of MPLS. So let's get on with it. MPLS, as the name suggests, it says that multi. Multi means multiple, right? Protocol. So multiple protocol. Switching. What does here switching means? So let's consider a router. A traffic on a router usually enters its one of the interfaces and exits out of the other interface. So we call the entering interface as an ingress interface, and the exit interface we call it an egress interface, right? Now the traffic is basically being switched from the ingress interface to the egress interface on the router, and that is how a router or even a switch is forwarding the traffic from the ingress interface to the egress interface. So here, this switching of traffic is basically done based on the labels. We will understand what is labels and how are they being used in MPLS in the later point of the video. So multiple protocols can do their switching based on the labels, and that is what MPLS means, multi-protocol label switching. Now, using MPLS, you can make use of your layer 2 technologies like spanning tree protocols, VLANs. So these are some of the features or protocols that we use in layer 2. These layer 2 protocols can make use of MPLS. Similarly, in our layer 3, we have routing protocols like OSPF, BGP, EIGRP, etc. So they also make use of MPLS. And in the OSI layer model, your MPLS layer or MPLS labels lie in between the layer 3 and the layer 2, and hence it is also called as layer 2.5. So MPLS was created with the purpose of faster switching of traffic. So as we were understanding how a router switches traffic from its ingress interface to the egress interface, it takes some time to do the processing of the traffic switching. So when MPLS was created, it was created with the purpose that the switching of traffic from the ingress interface to the egress interface will be faster. But now MPLS and your normal IP routing can do switching at the same pace in today's world. So before we get on to MPLS, let us understand how a normal IP routing works, how the switching of traffic in a normal IP routing works. Okay, so here you can see that there are 5 routers: R1, R2, R3, R4, and R5. All these routers are connected to different networks: 10/8, meaning 10.0.0.0/8 network. Similarly, 20/8, 30/8, 40/8, and 50/8 network. So let's imagine that a user from 10/8 network, that is, for example, 10.0.0.1 user is trying to communicate to a user in the 50/8 network, and the IP address is 50.0.0.1. So what happens is that when this user sends a traffic towards R1, right, it is received on R1's ingress interface. right? The first thing that R1 does is it checks for the destination network in its FIB, forwarding information base. Okay, it checks the destination network. The destination network is 50 slash 8. It checks for that network in its forwarding information base or FIB, and then with the FIB, it finds out the next hop IP or the next hop address, right? Next hop address. So with the next hop address, it also finds out its exit interface. Once its exit interface is found out, it checks the exit interface's MAC address in its L2 adjacency table, or you can call that as a MAC address table. So with that, it gets the MAC address. With the help of this, what happens is that it creates two layers of information. One is a layer 3 information where it will have a source IP with 10.0.0.1 as the source IP and destination IP as 50.0.0.1. Then it creates a layer 2 address where the source MAC would be the MAC address of this particular interface, right? For example, let us assume that the MAC address is AAAA, and in its L2 adjacency table, it will also find out the MAC address for this interface, R2's ingress interface, destination MAC, right? Let's assume that that is BBBB, and then what it does is it forwards this packet to R2. It forwards this packet to R2. R2 does the same thing. First, what R2 does is it checks the layer 2 header. In the layer 2 header, it finds that the destination MAC is its own ingress interface's MAC address. So then the next thing it does is it opens the layer 3 packet, and in the layer 3 packet it sees the destination IP address. With the destination IP address, again it does the same thing. It checks for the destination network in its FIB table. With the destination network, it gets the next hop for the destination network. With the next hop, it finds out the exit interface, and then with the exit interface, it tries to get the source MAC and the destination MAC from the L2 adjacency table. Then what it does, it rewrites. It basically rewrites everything. It rewrites your layer 3 header, R3, rewrites the layer 3 header once again, and then once the layer 3 header is created, it rewrites the layer 2 header. Okay, and then it forwards this packet to R3. R3 does the same check, it forwards to R4. R4 does the same check, it forwards to R5, and finally it reaches the destination IP address. So this is how your normal IP routing works. First, the router checks the destination network in its FIB table. With the FIB, it finds out the next hop for that destination network. With the next hop, it gets the exit interface. With the exit interface, it can now have two information, the destination MAC and the source MAC. So it finds out all this information in the layer 2 adjacency table, or we can call that as a MAC address table also. So with this information in hand, it creates the layer 3 header and the layer 2 header and starts to forward it to its next hop address. So this is how a normal IP routing works. So in your normal IP routing, a router basically has to do two things, right? It basically has to do two lookups. One is the lookup in its FIB table. The other lookup is in its layer 2 adjacency table. So MPLS was basically first designed to reduce the lookup of the two tables. Now, in order to reduce this lookup, MPLS uses something called as labels. Okay, and these labels are assigned to each destination network in the fib of a router. So what are the contents, the general or basic contents in a fib? Fib basically contains your destination network, right? Destination network information, the next hop address to reach that um, destination network, and also the exit interface, right? So this is basically just a small view of what's inside a fib. Now, in a fib, there are many destination networks, right? So let's say this is a destination network 1, 2, 3, 4, etc. There can be many destination networks. So when we enable MPLS on a router, it basically assigns labels to each of these destination networks. Okay, so let's say that the label example is A, B, C, etc. It assigns these labels to these destination networks. Okay, I hope you're clear till here how labels are being used, how labels are assigned to each destination network in MPLS. As we saw in our previous diagram, that MPLS assigns labels to each of the destination networks that is present in the router's fib. Okay. Now, if a router, if let's say R1, if R1 wants to reach the network 50/8, it should have the information or the information of the destination network. How can it get the information of the destination network? One is through static routing and the other is through a routing protocol. Okay. With the help of a static routing or a routing protocol, R1 will know how to reach 50/8. Right. Now, that is the first and foremost condition of MPLS, that end to end connectivity should be present from one destination network to the other destination network. Okay. Now, for each of these destination network that the router has created in its fib, it assigns label to them. So once a label is assigned to all the destination network in the fib, MPLS creates something called as LFib, which is called as label forwarding information base. This is a fib where you usually do normal IP routing, but once you enable MPLS, MPLS assigns labels to each destination network, and then it creates an LFib, label forwarding information base. As we have been talking about labels now, so these labels are basically assigned with a separate protocol. Okay, we do not use a normal routing protocol to assign these labels. We use a separate protocol for this. So the most popular protocol that we use to assign these labels is LDP, label distribution protocol. Label distribution protocol. Right now, there's another protocol which was the proprietary for Cisco, which was TDP, and it was called as tag distribution protocol. Now, since TDP was Cisco proprietary and it was not open standard, not many vendors used TDP, and it finally became obsolete. So TDP is no longer being used, and LDP is being used for distributing labels between the routers. So we will understand about LDP in some time. But first, let us understand how labels are assigned to each destination network, and we will also understand how labels are being exchanged between routers and how the switching of traffic happens with the labels. So here, let us assume that all these routers are running OSPF or any other routing protocol, and they are now aware of each other's destination network. Okay, so let us consider that in R1's fib, right, it knows in R1's fib, it knows how to reach each of these destination network, that is 10/8, 20/8, 30/8, 40/8, and 50/8. Okay. Now, obviously, since we are running a routing protocol, all these information, right? All these information about each of these destination network would also be known by other routers. So here I have just simply written the destination network that is known by each of these routers through a routing protocol. Okay, so let's not consider OSPF. It can be any routing protocol, or for that matter, and all these networks are known by each of these routers. I'm not considering right now, for simplicity's sake, I'm not considering these networks in between that are connected, uh, the links or the network that connects two different routers. Okay, so let us assume, okay, let us now assume that the each of these routers assign basically a label to each of these destination network. R1 R1 assigns a label of, for example, 11 to this, 12 to 20/8 network, 13 to 30 slash network, 14 to 40 slash network, and 15 label 250 network. Similarly, R2, R3, R4, and R5 will also assign labels to each of these destination networks. So here, as you can see that I have given different labels to the destination network in each of these routers fib table. Okay, so on R1 it's 11, 12, 13, 14, 15. On R2 16, 17, 18, 19, 20. R3 it's 21 to 25. R4 26 to 30, and on R5 it's 31 to 35. So these are the labels that each of these routers have assigned to their destination, to the destination network present in the fib. Okay, for simplicity's sake, let's keep all these labels differently. In real time, these labels may be same. On R4 and R3, the labels that they assign to each of these destination networks in real time may be same, may not be same as well. But for understanding sake, let's keep all these labels differently so as to avoid confusion. Okay, once these routers have assigned the labels to each of these destination network, they will exchange these labels with their directly connected neighbors only. Okay, so R1 can exchange the labels with R2, and so does R2 exchange the labels with R1, right? And R2 will exchange with R3, R3 can exchange with R2, R3 will do the same with R4, R4 will do the same with R5. Okay, so they all will exchange labels with each other with their directly connected neighbors only. So R2, if you see here, R2 will give its own label to R1, saying that I have assigned the label 16. I have assigned the label 16 for 10/8, 17 for 20/8, 18 for 30, 19 for 40, and 20 for 15. Similarly, R1 will also assign or exchange its label with R2. For R1, these are the labels 11, 12, 13, 14, 15, right? And R2 will also receive the same labels for R3, right? So R3 will exchange its label with R2 as well. So R3's labels are 21, 22, 23, 24, and 25, right? Now, similarly, R3 will receive the labels from R2, right? Let me Write that down here. That is 16, 17, 18, 19, 20. Right now, for R3 will also receive the labels from R4, right? So R4's label for the same destination network is 26, 27, 28, 29, and 30, right? So similarly, R3, R4, and R5 will also exchange their labels with each other. So here what I have done is I have labeled the router's name over each of their labels so as to that you are not confused. Okay, so on R2 here, if you see, the labels that R2 assigned is also mentioned, the labels that it received from R3 is also mentioned, and R the labels that it received from R1 is also mentioned, and their color codings are same, right? So you can pause the video and understand how the labels are exchanged between each of these routers, and how do they see this, so that you are not confused in the explanation that is going to continue now. So you can pause the video, understand how each of these labels are now present in the router's fib. Now this assigning of labels in their fib table is called as lfib, label forwarding information base. So this is basically how your lfib would look like. Okay, now let's say that R1, okay, R1 wants to send a traffic to 50/8 network. Okay, that 50/8 network is sitting here. Okay, and R1, not R1, a user from R1 is trying to reach a user in the 50/8 network. So let us understand how these labels are exchanged and switched from R1 till R5. So the user first sends the traffic towards R1. Okay, when R1 receives this traffic, it sees the destination network. Okay, and in the destination network, it sees 50/8 as the destination network. Now, in R1's LFIB, it has two labels for 50/8 network. One is 15 that it assigned itself, and one is 20 that it received from R2 for 50/8. Which label should R1 assign and forward this traffic? Okay, what R1 does is R1 basically assigns the label that it received from R2. So the concept here is that, let's say that there is a person called Bob, right, and the other person is Charlie. Okay, now when they two meet for the first time, okay, they introduce each other, right? They basically introduce each other. Bob says, "Hi, I am Bob." Okay, and Charlie says, "Hi, I am Charlie." So basically, whenever Bob has to talk to Charlie, he will call out Charlie's name, not his name, right? So similarly, the labels are also like that. R2, okay, R2 basically tells R2 basically tells R1 that I have assigned the label 20 for 50/8 network. So if you want to send a traffic for 50/8 network, assign the value 20 to it. Assign the value 20 to it and then send it to me. So these labels are called as local labels meaning the labels that are assigned by the routers, and remote label, the label that are received from the other router. So this is the remote label. These are the remote labels on R2. On R3, these are the remote labels, meaning the labels that it received from the other routers, right? So these are all their remote labels. So they will only use remote labels to forward traffic. Okay, and they will use local labels to exchange it with the nearing or nearby router. Okay, so moving on with our example here. Okay, so the user wants to reach 50/8 network. R1, upon receiving this traffic, it checks what label has it assigned, has it received from R2 for this network. So it sees that R2 has mentioned that I should use 20 label if I want to forward this traffic to R2. So basically, what it does, it assigns it assigns 20 label to that traffic and forwards it to R2. Okay. R2 then sees that it has received a label. Okay, it has received a traffic with a label of 20, and it then checks in its lfib. Okay, so these are all the lfib for each of the individual routers. So it then checks for lfib, in its lfib, that you know what label has it used for the corresponding destination network that it has received the label for. So it sees that I have received a label of 20. To which destination network does it belong to? It belongs to 50/8. Okay, now I need to forward this traffic to the next hop. The next hop is the R3. Now, what label have I received from R3 for this destination network? So what it does, it swaps the 20 label with 25 label. It swaps the 20 label with 25 label because 25 was the label that R3 assigned for 50/network in its lfib, and it has shared the same label with R2, saying that if you want to reach 50/8 network, you assign the label 25 and forward it to me. Okay, now this 25 is then forwarded to R3. R3 sees the label 25 being received. It checks to which destination network this 25 corresponds to. It sees that label corresponds to 50/8 in its destination network. Then R2 does the same. It swaps 25 with 30, which is the label that R4 has assigned for 50/8 and has exchanged it with R3. So R3 swaps this label with 30 and forwards it to R4. R4 does a similar check, then swaps the label with 35 because that's the same label for R5, and forwards it to R5. R5 checks the label as 35, and then it knows that the label is for 50/8 network, and it forwards the traffic to that user. So here we saw how labels are being swapped or switched from one label number to the other label number. Okay, so there are few things that we have to understand what is going on. Okay, the the first thing is that the remote label is used to exchange, switch, or you can call it switch, or you can call it swap the traffic from the egress interface, from the ingress interface to the egress interface. Okay, local labels are basically used to tell, okay, they are assigned in the fib, okay, and they are exchanged with the other routers with the expectation that this local label will in turn become a remote label in the other routers lfib, right? Local label is for its for the router's own judgment of forwarding the traffic, right? Remote label is the label that it assigns and then forwards the traffic. I hope this was clear here. Okay, now there are a couple of things or terms that we have to understand before we move on. So those terms are ingress, egress, etc. So you can see them that I have noted down here. So the router, okay, the router in this scenario, if you see in this scenario, the ingress router is basically the R1, okay, meaning that it is where the MPLS is starting, okay, or ingressing or entering the MPLS network. So R1 is called as the ingress router, okay. Then we have R5. R5 is where the traffic is exiting the MPLS network. So it's called as the egress router. What about these three routers here? Okay, they are called as label switch routers. Okay, so their work is to basically switch the label in the ingress and the egress interfaces, right? That is why they are called as label switched routers. So the ingress and the egress routers are also called as label edged routers because they are sitting on the edge of the MPLS network. That is why they are called as label edged routers. Okay. Now, there are a couple of things that we understand with the routers. Now, there are few names that are also given to these labels or the switching of the labels. They are push, swap, and pop. Okay, what does push mean? So, in our example, when the traffic was received by R1, right? So, R1 checked the destination network and it assigned a label to that particular traffic using the destination network. So, basically, it is pushing a label to that traffic. Okay, and these routers, the label switched routers R2, R3, and R4, they basically were swapping the labels from one label to the other label, right, inside them, and then forwarding the traffic, right? So that is called as swapping of labels. Now in the end, R5 received the traffic and R5 has to basically remove the label so that it can forward the traffic in normal way to the 50/8 network. So it is removing or popping out the label from the traffic. So these three terms, push, swap, and pop, is how the labels are switched from one MPLS network end to the other MPLS network end. I hope these terminologies were clear to you. So till now we understood what are labels and how label switching is done using push, swap, and pop. Now let us understand about the label distribution protocol and how it basically works. Okay, so label distribution protocol is a layer 7 protocol and it uses UDP and TCP both with a port number of 646. Also, it uses a multicast address of 224.0.0.2. Okay, now let's understand how basically this works. When you enable MPLS, okay, so it's like MPLS IP, sorry, MPLS LDP, when you enable this on a global level, globally you can enable this on the router. Also, per interface, if you want to enable, you can use the command MPLS IP on per interface basis to enable MPLS on that particular interface. So anyway, whenever MPLS is enabled, okay, let's say that on R1 I enabled MPLS. So what R1 basically does is it starts to send hello messages, MPLS hello messages in every 5 seconds. Okay, at the multicast address of 224.0.0.2 using the UDP port 646. Okay, and along with this, it will also send its own label distribution ID. Okay, label distribution ID, or you can call it LDP ID. Okay, now what is this LDP ID? LDP ID is very similar to your router ID. Basically, it tells the ID of that particular router which sent the hello. So it is also elected in the same basis, where it is the highest loopback that wins the ID election. If there is no loopback created, then the highest physical IP address wins as um, the highest interface IP wins as the LDP identifiers election. Okay, so now let us take an example here when where R1 is enabled with MPLS, and it sent out a hello message. In the hello message, it sent out its um, identifier. For example, let's say that the loopback address on R1 is 1111, and on R2 it's 2222, right? So in the hello message, it sent out the hello message along with its hold timer. Hold timer is basically 15 seconds. It sent out that, as well as its own LDP identifier. This is sent to R2. Upon enabling MPLS on R2, R2 receives this hello message from R1. So now R2 knows the LDP identifier for R1. It also sends a hello message to R1 with the same criteria, but the LDP identifier here is 2222. Now R1 also knows the identifier LDP identifier of R2, that is 2222. So once this exchange of hellos is done, okay, on a UDP basis, they start to send a TCP connection with each other. Okay, then that is how a TCP connection is started using the LDP identifiers that they found out using their hello messages in the MPLS LDP message. Okay, now in this TCP session, after your three-way handshake is completed, they create their LDP bindings or labels for each of the destination network in their fib, and that is how your LFIB is created after your TCP connection is complete. Okay, so this is how your label distribution protocol basically works. Now let's come to a scenario called penultimate hop popping, which is commonly called as PHP. Okay, so consider that this is our MPLS network, and on all these interfaces, your MPLS is enabled. Okay, so what happens is that if a traffic is sent to R1, then what it does is it pushes the label, and it forwards the traffic to R2 and R3. They swap the traffic, sorry, they swap the labels, and then they forward it to the next hop, right? Here, when that particular label reaches R4 then sees that the destination network that that particular label is associated to does not have any MPLS enabled on that particular interface also. So basically what it does, it pops the label, right? Now here, basically what R4 does is R4 first checks in its LFIB, right? For 40/8 network, has it assigned any labels to it? Okay, after that it has to pop it because that's the destination network, and then once this popping of labels is done, as I was saying, the your MPLS label is sitting in between layer 2 and layer 3. Okay, so the first thing that your R4 does is it checks your layer 2 information, and then it checks the labels, and in the labels it does a popping. Once it does the popping, it then has to do the same lookup for the destination IP in the layer 3 header. So basically your R4 is doing two types of lookup. One is the lookup for the labels, right? If it's the last label, and once the label is popped, it does the lookup for the destination network in the layer 3 header. So there are two types of lookups. Okay, now in order to avoid these two lookups by the LER, label edged router, we came up with a solution called as penultimate hop popping. Okay, it's basically called penultimate hop popping. So here what R4 does is for 40/8 network, because it's directly connected, one, it does not assign, okay, does not assign any label, okay, and exchanges this with R3. So R3 knows that if it has to reach 40/8 network, that would be the end of the label. So basically R3 would remove the label, R3 basically would remove the label, and then it will forward it to R4. Okay, so R4 basically just has to do one lookup, that's the destination network addresses lookup. Okay, now when R4, or for that matter any router, okay, for the networks which is their end network, they do not assign label. But until unless there is a label assigned, how will the other router know that it has to basically remove the label, right? And that particular label where the label is not assigned is called as implicit null label. Okay, and the value of implicit null is basically 3. Okay, and the value of implicit null is basically 3. Okay, so for 40/8 network, R4 sends a label or an implicit label as 3, right? So R3 knows that if it has to forward a traffic to 40/8 network, okay, and that 40/8 network has an implicit null value of 3, it basically pops. Basically here R3 pops the network, sorry, R3 pops the label, and then forwards the traffic to R4. Okay, here it is basically a normal IP forwarding that is being done. Okay, it's not the MPLS switching of labels, but a normal forwarding of IP traffic. And then R4 sees not the label but the layer 3 destination IP address, and then it forwards the traffic to 40/8. So in this video we learned what is MPLS, right? How labels are exchanged, how LFIB is created, how push, swap, and pop is done using those labels, and how penultimate hop popping helps in avoiding two types of lookup at the LER. So in the next video, we will look into the practical of MPLS with Wireshark so that we can understand the even minute details inside MPLS network or MPLS traffic that is being switched from one router to the other router. I hope you like this video. Please do subscribe and share this channel with others. Thank you.